that illustrates, running Feast from within a Kubeflow cluster. There will be parts that I'm not going to demo that might take too much time to fully, deploy and wait for and spin up. But I think once we've gone through that complete notebook, you'll get an idea of, how you could use Feast with Kubeflow, and then just discuss like, where the project is right now and where we're going. So the machine learning lifecycle prior to a feast or feature stores is something like this. Some business, some data scientist in a company or some business person decides that data can improve some outcome for the business, and they're given a task of doing some exploratory data analysis, figuring out based on the data if they can produce a model that can eventually be shipped into production, and become essentially a decision system within that organization. So what we often find is that the data scientist is the one driving the process, and they start with the notebook, they start with EDA, and they know that they need to get into production one day, but they don't really think about that until it's like a final step in the process. So naturally, start with the Jupyter notebook, and that creates a flow, and you can think of that as a graph, or however you think about that. It's a monolithic thing that often resembles the final product that you create. And if you look at a lot of online tutorials, you'll see, toy examples of productionizing machine learning is often a notebook that is evolved towards multiple components, but they're still monolithic. So it's taking data from some sources like a data lake or streams or a data warehouse, doing some processing, training a model, so future training a model, deploying the model, and then model serving. And often, in the worst case, pathological cases that I saw at Gojek was it's just one big pipeline. And even the training and the data transformation is one part, is a multiple nodes in the Airflow graph, and the deployment is like the last step. And this is often good enough to get into production, but this comes with a lot of challenges as well. So these kind of 5 challenges that we identified. One is that monolithic ML pipelines like these, they're easy to get into production, they're easy to reason about, but they're very slow to iterate on. So often you have one group doing data, for a large project, one group doing data transformations. You have another group iterating on different kind of models, different kind of parameters, and then you have another group doing model serving, the production aspects, and the everything around the operational facilities of that model. So you often want to, at scale, iterate independently on these dimensions. And especially for data being 70, 80% of the value that you get out of the model at the end of the day, you want to have teams cross-pollinating the projects, their own projects, even with the same features or features from sister teams or adjacent teams. And so being able to independently iterate is very important, but it's also very hard in the kind of monolithic structure because by nature, by definition, you're siloed. One of the other problems we saw often is features are developed for training, and it's written in Python, and you can ship a model, but then in the serving environment, those features don't exist, and they need to be rewritten in Java or Golang or some kind of more performance system, maybe Spark structured streaming or Flink or something, and that creates inconsistencies. And that's one source of inconsistency, but there's a third problem: is many types of different inconsistencies that you find between training and serving. And so rewriting features is one of them, and you can also have things like feature leakage and training serving skew introduced by many different factors, because the feature store is essentially a system that sits between your data engineering world and the production world. And those environments are by design often built to be different. So you have higher standards in the production environment, more controls. Often those are the sources of truth there. The events are being produced there. And in the offline environment, you might not have the same copies of data. You might even have synthetic data. And so there's many different reasons why those inconsistencies occur. And the fourth problem you often run into is data quality monitoring and validation is absent. And especially find this at a lot of like smaller teams or teams that are just starting on their ML ops journey. They don't have tools that allow them to validate data prior to training. Data from upstream teams is often one of the biggest problems you see is that you depend on a database or a warehouse that another team, like a business intelligence team or some kind of warehousing team, has built. But if a table breaks there, you don't know if a stream stops getting clickstream data. You might not know until it's too late. And so data quality monitoring is absent, but also the monitoring and validation is built for, it's not built for machine learning. It's not built to, look at the distributions of data. And so data quality monitoring and validation is something that's also quite critical and a big problem that we see. And finally, just to get this ties back to kind of the iteration aspect, is there's a gross lack of reuse and sharing amongst teams. And this is kind of more an organizational problem, but we believe technology can help with solving this to some degree. If you facilitate discovery of features and discovery of data, and then also, I guess, there's an aspect of trust as well. So if you can trust that you can rely on somebody else's feature and that they can't just break that and cause a production downtime for your system, then you're more likely to use that. These are some of the kind of high-level problems that we identified with this kind of like evolution of a notebook into a production system, and teams that are kind of like early on in their MLOps journey still. So Feast is a system that attempts to solve some of these key data challenges with production machine learning. It doesn't solve all of them, and today we're going to go through some of them that they solve. And we can talk about the things that it does well and the things that it still not doesn't do well. And at the end of the talk, I'll also talk about, give you a preview of what are the things that we are working on, for the next couple of months. So prior to Feast, this end-to-end flow is something like this. There's like some sources, some transformation of data, there's model training, there's deployment, and there's also almost always an online store where you're serving features from, and that's where your model is retrieving feature. Your model serving is going to retrieve features from in a production environment. When you introduce a feature store like Feast, this process kind of splits up a little bit. So you have three main areas of iteration. One is the creation of features. So something that's very important to call out here is that Feast is a way for you to productionize and operationalize your existing features. So we're not trying to reinvent Spark and Pandas and all these kinds of transformation tools. And it's a very competitive space, and it's a space that we think is not our core competency. We see a lot of problems that are not being solved that are even more important than the data transformation. Not, I wouldn't say more important, but they're less addressed in the data transformation aspects. So we basically rely on upstream systems like Spark or DBT, stream processing engines like Flink, to do transformation. So we say, use your stream, transform it there, take your data lake, transform your data there, or take your warehouse like BigQuery or Redshift or Snowflake and transform your data there. And we're going to be the layer that you can you need to define your definitions, and then you can kind of like slot onto your existing sources of data, and then we can operationalize that specifically for machine learning. So this create feature step is that step where you can do that operationalization. So once you've registered your sources of data with Feast in that first step, then you can go to training a model. And in the second stage, you'll query the Feast API. You can use things like listing features, listing entities to discover which features your team or another team has created. Select some of those that are applicable to your model, and then train your model. And then you can store your model in an MLflow or some kind of artifact store. And what we often then encourage people to do is, you train your model, and I'll show you a little bit later what this looks like. But you can train your model, and you can just store a list of the feature references. And so Feast has like identifiers for features, and you can persist those as with the model binary. And then when you're ready to productionize this model, and you can store hundreds of iterations of how many of your models you want to train with different features and different parameters. When you pick a model to deploy to prod, you'll take it out of machine learning MLflow, and you'll ship it into your model serving container. And for the most part, depending on, of course, how complex your data structures are that are being sent from the production system, you can commoditize your model serving layer almost entirely, because you'll have a model binary that's going to be hosted in that model serving. But the feature lookups itself is just going to be a parameter, and that parameter is going to come from this file containing a list of features. And so when an incoming request comes from a production system, there's a client in your model serving that calls out to Feast based on this configuration, gets the online features from the online feature store, and serves that to your model, and then you can send out your prediction back to the production system. So these are the three main flows. One's creation of features. The second one is querying Feast for training data and then training the model. And the third one is just querying Feast to get online feature data. And the final one can be completely commoditized. So what does Feast provide? So Feast provides a registry. It's a common catalog with which you can explore, develop, collaborate, and publish on new feature definitions. But these feature definitions you can kind of think of them as schemas. They're not transformations. That's not, your pandas and your PySpark. If we can talk about some of the other feature stores and how feast is slightly different from them, but this registry is essentially a schema registry that allows you to define where your sources of data are within your organization, for you to track those and for you to kind of add metadata about those sources within your org. Feast allows you to ingest data, and you can do this from both batch and streaming data sources. And so one of the great things about feature stores is they can completely decouple your operational machine learning environment from your, kind of the breadth and diversity of the data sources that you have in your organization. And Feast with feature tables, or these are the definitions that you store in the registry, allows you to map those sources into the system. But it keeps your models abstracted away from them. It kind of like decouples those models completely. So your models only see Feast, but behind that you can have a rich variety of data sources. And ingestion is one of the ways that we preemptively load data from those sources into stores like an online store or an offline store, so that when your models need data, that you can just query it from those stores at like low latency or more scalably. What we also do is allow you to kind of federate over external sources. So if you're using BigQuery, we don't expect you to move your data from BigQuery into some other location, like a bucket. We can just leave it there in BigQuery, and then we can build training data sets from that source. So once you've ingested your data, Feast also allows you to do serving. So this is a feature retrieval interface that we provide for you, and it creates a consistent view of your data. And essentially, what the feature store is going to do is provide it's kind of like the interface between your models and data. And this serving interface fulfills one key requirement, which is consistency between training and serving. So when you hit the training interface, it's going to be an SDK call with list of features and an entity data. We call it a spine or an entity data frame, and we're going to enrich that spine or entity data frame with feature data. And I'll show you a little bit later what that looks like. But when you call the online serving interface, when you're doing your predictions online, it will be the same list of features, and it's going to get the latest versions of those features back. And this is critical for ensuring that the models behave in the same way and optimally in production. And then finally, Feast also provides monitoring. So it'll produce metrics and statistics, based on based on interfaces that we expose to you, as well as like part of the ingestion jobs and part of the serving API. So, if you're an engineering team, this is not just a black box. It will emit metrics that integrate with your existing systems like StatsD and Prometheus and all the tools that engineers are already familiar with. So what is the high-level flow that you can expect Feast to execute? So typically you'll have your data sources on the left, your streams, your data warehouse, your lake, or even notebooks where you're kind of iterating on your data. You can have an Airflow pipeline, anything arbitrarily where you're working with data. Then we have an ingestion layer, and so what the process is that you typically follow is that you interact with the core registry, and you define some kind of feature schemas there. And then you would ingest or launch jobs that load data into the stores. And in this case, it'll load data into the online store. For the latest version of Feast, we're moving towards mapping onto your existing data sources. So we've actually removed the historical feature store. And to some degree, we've removed it, but it's more a semantic thing because we're basically moving it upstream to be a data source. That avoids us from creating data islands within your organization and creating siloed data. So we just want to map onto your existing data sources. So basically, your ingestion into the online store. Today we support Redis there, and then there's going to be a kind of two ways you can retrieve data. You can build queries that execute over your existing data sources for building a training data set. So we'll just launch a Spark job, and this will query either S3, GCS, or BigQuery and build the training data set for you. And then in an online case, we've got a feast serving API that you can query with your model serving services and retrieve online feature values. We also have statistics APIs where you can produce TFDV based statistics. We're probably going to be moving towards great expectations going forward, but that's something that we think is going to be a big part of our feature store over the next couple of months. So what's Feast not? So Feast is not a workflow scheduler. It's not an Airflow or Luigi. It's not like Pachyderm and some of those tools where it's it doesn't do pipelining or versioning. I think that's the fifth point. Um, it's not a data warehouse, and I think this is something that is often super confusing to people, where the feature store name is kind of so overloaded that, and there's so many feature stores right now that it's hard to know what a feature store does and doesn't do. But we don't see storage of data as our core competency. For us, the key thing that the feature store provides is a consistent view of your data to models, because machine learning is, I think this is one of the things I said earlier about we're solving, ML specific data challenges here. And machine learning has this requirement of training and serving, or models need to be trained and then served. And there are multiple problems there, but just for that specific one, you require a consistent view of data between the two worlds. And that we see as our core value prop. Everything else is kind of layered on. And so it's data quality monitoring, or if it's integration with model serving libraries, or if it's integration with upstream data sources, those are kind of extensions to the system. So we're also not a data transformation processing tool like Spark or DBT or Pandas. We're not a cataloging system or discovery system like a Munson or Data Hub, although those systems integrate with us. And I think Munson and those folks have gone to great lengths to integrate with Feast, and there's some good blog posts out on if you want to use these two together. Like I said, we're not data versioning or version control or lineage system. I think that we play a big part in that lineage and version control. And I think David Aronchik is in this call. He's going to definitely say something about that. But you can't have an end-to-end machine learning system where all the components are not logging the artifacts that they produce and the inputs and outputs that they have. Ultimately, you're shipping models into production, and those models drive business outcomes, and you'll be tracking those models. And if something goes well or something goes badly, you want to be able to trace back through that model's history why it performs the way that it does. And if you have a black box in a feature store, that's not going to cut it. So yeah, we are not the ones pushing the kind of lineage problem forward, but we definitely produce the artifacts and the information that those systems need to kind of dissect what happened to a model. And of course, we're not model serving or metadata tracking, so we're not like MLflow or KF serving or Selden, but we play very nicely with those tools, and often KF serving and MLflow are used with a system like Feast. So let me do a quick demo just to kind of take you through one of the notebooks that I prepared. I'm going to give you a bit of a background on where we are right now with Kubeflow and Feast. So the things, with Kubeflow are, it's not super easy to install, just to be super frank. If you go to the Kubeflow website, you'll see that, let me even just take you there right now. You can see components, feature store, and you'll see the Feast documentation here. And if you want to get started with Feast today, we link you directly out to our own docs. And so technically, yes, Feast is a Kubeflow component, but the experience is not super sleek yet. And that's something that we're really working on. So I've got a pull request that I submitted a few weeks ago. It's closed right now. There's one that's open that explains it, but this specific pull request, anybody can follow, and it comes with a Jupyter notebook that shows folks how they can actually use Feast and Kubeflow together. So essentially what you do is you can do this completely locally. You can start a Minikube instance. You can there's these YAML files called KF dev files that Kubeflow uses to deploy a complete stack, and I can even give you a quick glimpse of one of them. So there's all these variants that are cloud specific, IBM, Azure, GCP. There's even completely on-prem ones, and that I took one of these and I extended it for Feast, added Feast to it. And so the pull request we're working on right now is to include Feast as a core component within Kubeflow and make it super easy for teams to get started. And the idea is that you just install one of these stacks depending on the environment that you're in, and you configure your components in the way that you want to use them, and then just use them. And so Feast would slot in there very nicely. We'd reuse the existing components within Kubeflow, like Spark, like Minio, like the databases, and then you can just use Feast for your online retrieval of features or for your training from a KF pipeline or a KF serving component. So I've already installed one of these, and I can take you to it right now. But at the end of this, I'll link to this PR where you can see the complete process. This shouldn't take you more than, I think, 10 minutes to set up. But there are some specific individual steps that you need to do to enable service accounts for the Spark operators. So I've already
Hey
gone through this
Willem,
process, and you can still see my
Willem,
screen, right?
before you jump into that, I might break your flow real fast,
Go
but
for it.
there was a question about, is there a clear, unambiguous concept for feature engineer?
Like a concept for a feature engineer.
Yeah, or I wonder, so this was from Victor. Victor, let us know in the chat if you're talking about feature engineering or an actual person that is a feature engineer. I'm not sure if I understood that correctly. I get the feeling he or she wants to know about feature engineering.
Yeah, I mean, we don't really treat feature engineering as completely different from just data processing or data engineering. It's basically just any kind of data engineering that leads to, rich data signals that will be used in models that drive some kind of, predictions or inference.
Nice. All right.
And yeah, let's leave it there. But feel free to
Yeah.
follow up with another question if you want more specifics there. Um, Yeah, so I've already set one of these ones up, and if you go down, I've got like a VM that I've set up, and I'm just running Minikube here, and you can go kubectl, get pods, kubeflow, and so basically, if you run the commands that I illustrated on that note, that pull request, you'll end up with one of these. You'll end up with a complete cluster. Okay, then one of these slaves and crash loop back off, but we can ignore that. It's fine. Um, and it'll be a Kubeflow installation. This is completely an on-prem installation. I think the only thing that is not on-prem here is, or not completely open source, is just we're going to reference a bucket on GCP, GCS. But you'll see that we've got the a feast stack deployed here as well. So there's a core registry, there's a job service, we've got the metadata store, and we've got an online store running here as well. So what we're going to do is we're going to run through a notebook that I've set up already. But when you go through that guide, you'll spin up your Minikube, you'll install Feast and Kubeflow, and you're going to be presented with an interface like this. This is just a normal Kubeflow interface. You can just go to the notebook servers, create a pod here. So you create a new notebook server, and then you can connect to that. And when you go into that, you can just download this Feast on Kubeflow notebook that I'll link to at the end of my presentation. And I'm going to walk through that in a second. And I've already got it set up over here. So basically what we're going to do today is just, I'm going to click through this. There's some parts I'm going to, not spend too much time on because, Spark compute can be a little bit slow. And I'm trying to show you how you can reuse, some of the Feast components like the Spark operator that's built into that's built into Kubeflow. But you can also use things like Dataproc or EMR or other kind of Spark environments if you want to do ingestion of your compute. And sometimes they're going to be a little bit more, performant and faster. So basically what you do is you'd install the Feast client. In this case, what we're going to do is we're just going to create like a staging bucket. So I'm creating a new one right now. Pull in your Feast dependencies. And if you install it, it's just something simple as pip install Feast to get your Feast installed. Now, of course, the current Feast requires you to have, it's kind of a client server model. And so it expects a Feast deployment to exist behind the scenes. So it's not completely a client. But this is something that, we're trying to question. Do you actually need to have a complete deployment on a Kubernetes cluster to operate a feature store? And something that we're thinking about, how can we get around that and make it easier for data scientists to just get started with the pip install? So you'd import your Feast and some of your dependencies. You'd create a Feast client, and this client allows you to interact with the deployment of the feature store. And so here is your feature definition process. So at this point, you've got some kind of data upstream. You've got your data in a warehouse, you've got data in a bucket, or you've got data in a stream, and you want to pull that data into the feature store in order to serve it to your models. Now, if you're coming from a data science environment, often if you're just doing batch, the value prop is not high. And you can often get away with, just creating training data sets in a, SQL and BigQuery or in your existing database or somewhere else. But if you're trying to do online serving, then it's kind of important to have a kind of production grade feature store that serves features to your models in an online environment. And so, mapping these schemas and the sources into the feature store and providing that consistent view is critical. So what we do here is we're going to go through a ride-hailing example, and I've created a driver entity here, and so it's just an entity definition. It's super simple. And this is going to be the key that we join on. We've got some features. Some of them are daily features. Some of them are real-time features. These are not real features. We're just going to kind of use synthetic data here, but you'd create feature objects. We're going to use the staging bucket that we just created to kind of stage our data. That'll be a kind of synthetic data source. And we create these feature tables, and these feature tables are kind of the key concept within Feast, and it's a schema that defines where the structure of your data is and where to find that data. And feature table can have perhaps just a batch source, maybe it's just batch data, but a feature table can also have multiple sources. So it can have both a streaming representation of the data and an offline batch representation. And so if you're building a training data set, we'll hit the batch source and build your training data set from there. But if you're running this in production, we'll also provide or provision a streaming job that streams in data from your streams and into your online store so that your features are always staying fresh. And so you create two of these feature tables, and you have your features listed there. You'd have your entity, and you define your file source or your Kafka source or your batch source or your BigQuery source or whatever source you have. There's still some limitations here. We don't support every source type, and we're trying to expand the amount of sources and stores and connectors that we have. But today we only support Parquet and BigQuery as the two sources here, and Kafka and Kinesis as the streaming sources. And there's variation on the kind of like formats and file types, but for the most part, those are the primary ones we support. And so you register these with the registry. It's literally just the client apply method, and so it's idempotent and it's registered. And then you can get those back, and if you just print those out, now the feature store knows about those feature tables and the data that exists. And we've also got some metadata that we return, like when the feature table was created.
Hi William, sorry to interrupt. Can you enlarge the font a bit?
Sure.
It's
I
kind of small, too hard. Okay,
Okay.
it's much better. Thank you.
Okay. Yeah. So just taking you back there. You all can see this, right? Is this a bit clearer?
Yeah. Yes, it's much better.
Great. Okay. So you've registered these feature tables. So literally just name, entities, and this is going to be the key. This is the features and your source. And once you've registered them, we can see that the Feast knows about these and they're officially registered. So at this point, there's two steps that you still need to go through. If you're running a job service, it'll automatically see these definitions, defined, and it'll start provisioning jobs. So it's going to start spinning up Spark jobs to stream in data, or it's going to start backfilling your online store. So in this case, we're not enabling the Spark job service, even though it's deployed. I'm going to take you through how you could manually do an ingestion. And I know an ingestion is not something that, in this notebook, something a data scientist would do. It would be typically something that an engineering team, kicks off from, CI. So how we see teams do, use Feast is these feature table definitions are stored as YAML in a Git repository and version controlled. And then every time a data scientist or somebody wants to make a change, they publish a new feature table as YAML, and that would kick off, a new ingestion job where it would apply this schema to the core registry, and then from there a new ingestion job would be kicked off. Is everybody still with me, or are there QA questions?
There's questions.
Okay.
For sure.
If you want to take a break here and maybe answer some questions, I can do that.
Yeah, let's do a round. So we've got one from Mark asking about how Feast ensures that feature transformation in batch are consistent with those done in streaming ingestion.
So yeah, so that's kind of a tricky one right now. In the old Feast, we used to have a unified ingestion layer where we had kind of one streaming entry point into the system, and so you automatically ensure that everything is consistent because everything has to go through that one point. But now we're offloading that responsibility to upstream systems, and so you have two entry points, the batch and the streaming one, and in theory those could deviate. So there's no real way that we can, unless we are doing the transformations, ensure that you're producing the same data there. All we can do is kind of the kind of term negative engineering, where we provide you with ways in which you can react and identify those problems. But if you have kind of a raw event lake, and this is something that Tecton does with its feature store, like events in a data lake and events in a stream, those are relatively they might not be ordered in the same way offline and online, but they are relatively immutable. And so if you do the transformations, you can ensure that consistency. Um, but if you are just kind of bolting on other systems, it's very difficult to ensure that consistency. And it's something that we're kind of trying to figure out still. The likely direction that we're going to go is also be the ones that log the data from the stream into the offline environment. And so then we do control that to some degree. But if there's an external system that is doing transformations, then it's kind of hard to ensure that.
Yeah. Awesome. Next up is from Diana. Can Feast connect with Google, AWS, Microsoft, IBM Cloud, machine learning platforms?
Yeah, so we have Terraform scripts that allow you to deploy. Well, Feast can actually run anywhere because it's completely open source today. So so it doesn't have any cloud dependencies per se. You can use Minio and Spark operator to run it. And so the question I'd say is more, is there a native experience where it's like super seamlessly slots into your existing, tech? For GCP, we've got BigQuery support, so you can deploy GCP on a Kubernetes GKE and just use it there at BigQuery. For AWS, we use Kinesis, and we just can use EMR, and so that's something that some teams are running as well. And we extended support for Feast on Azure, so we support Azure blob storage, so it works there. And recently, the IBM folks have also taken a stab at porting us over to IBM. And I think Ted Chang and Animesh, some of the folks that are big contributors in Kubeflow, have taken a stab at that. And there are some docs for that. It's a little bit experimental, and we're not 100% sure if there are still some rough edges there. But in theory, that should also work. Yeah. So you'll have an API at the end of the day that you can call from your existing model training or model serving environments in those clouds. And so yeah, the answer is yes. But GCP and AWS are the ones that we've actually run and tried out at scale, but we haven't really. Azure and IBM are a little bit more experimental and newer.
Nice. So we've got a few more in here, and then we'll let you get back to doing your thing. Alfred was wondering, will Feast be able to train on non-stationary data sets?
What does he mean by non-stationary?
Ooh, good question. Alfred, if you're out there, please let us know in the chat what exactly you're talking about with non-stationary. And in the meantime, while you're typing that in there,
I mean,
Alfred,
if he means like there's a table where, it's always a pending data, and, if he has to query that table, that's entirely possible. And, we log the kind of like parameters and metadata about the range of data that we pulled in to pull the training data set. So you can see that information, but, if the tables underneath Feast are changing, then, there's always going to be a problem of, the output results changing. And what we find is that there's no clear answer of which one is better or not, because some of the folks we've worked with have hundreds of millions of events in a table, and they can't afford to duplicate that. And without duplication, it's a very hard problem to solve. Yeah.
So, Alfred, if that answered the question, let us know. If not, we'll give it another crack. And the last one in here from Himant. So a feature store is similar to a data model schema repository used with traditional data systems.
I think the feature store requires the schema repository in order to function. But a key thing about the feature store is that it's a production operational system. It serves data. It serves very, very large amounts of training data to your models in a distributed fashion. And it serves online features at very, very low latency. And so that is slightly different from just the schema repository aspect of it, but it's a component of the store. Yeah.
Excellent. So Alfred's saying you answered the question, and I guess that lets us get to the next part of this. Let's keep rolling.
Cool. Okay. So now we've got a bit of code that is kind of janky and, it's just for illustrative purposes. We're just going to create some synthetic data and I'll just click through these, just running these cells. So we're just going to generate some fake trips, some fake statistics, and, some fake data frames. And it gives you an idea of like what we're dealing with. So you have like a driver ID. There's some conversion rate. That's like how many of the trips the driver's done that were successful. What percentage of trips do they accept in a typical day? How many trips do they do in a day? Obviously, this is fake because you can't do 1,000 trips a day. But this just gives you an idea of like some numbers that you typically work with. So then we do an ingestion. So this is a kind of backward compatible method that we kept in Feast that we may or may not continue to have in the future. But essentially, you need to have your data at the location where Feast expects it to be. And so this ingest method is writing the data to that source location of the feature table. Typically, it would be slightly different how this works. Typically, you'd have an Airflow pipeline where you'd have some process that creates your data and puts it into like a BigQuery table or Snowflake table or somewhere. And you wouldn't need to do this ingestion because you're already doing it with your existing pipelines. Then for historical retrieval, one of the things you need to do there is you need to have an entity data frame. And this is what an entity data frame looks like. It's literally just the driver IDs and event timestamps. So we're going to make a prediction based on driver IDs as our key, as our entity. And so you just want to have a list of those and timestamps. We call this an entity key. And this is this structure, this data frame is called an entity data frame. And basically this often is these rows represent observations, and typically you'd have an outcome that based on this observation. Like at this point in time, you knew that the driver had the thing that you're trying to predict, like if it's conversion rate or if it's acceptance rate or whatever it is. That is the point in time in which you know it. And it's very important to know that this timestamp often doesn't correlate with your features. Your feature will be calculated maybe on a minute, hour, day, weekly basis, and their timestamps will be often floored or ceiling to some kind of like round number. And so part of what the feature store is going to provide is a way for you to join all those features in a point in time correct way and enrich these kind of rows that are essentially observations. In a way that you don't have to deal with the timestamp mapping, and it also prevents you from doing unnecessary feature leakage and some of the traps you might fall into. So you could just have a feature list, and this list is just the feature table that we defined earlier, and the list, kind of like the value is, sorry, the feature reference consists of two components, one being the feature table and the feature name itself, and this list is the list of features that we want to train on. So we just use this, we create a query to the feature store to pull this training data set, and you just provide your data frame, the one that we defined up here, entities with timestamp, and the list of features. And this is going to take a while. This is going to run on Spark on Kubeflow, and we're going to wait for this output file URI to come back, and this is just going to give us the location of the training data set. So if we go down here, I think we can even go to, let's just see, kubectl get Spark application. I believe it's going to have a Spark application. Yeah. So 23 seconds ago, we saw that one jump out at us. Let's just describe it. And so there you have it. It's the job is running, and now you're building a training data set. And what will essentially happen is, this job is going to go to this bucket that we just created at the start of the notebook. It's going to find all of those, kind of like raw feature tables. So just to kind of like map this back, typically you'd have a ETL or ELT system that's producing data, and you already have your tables. So in most companies or most teams, might be a different team's data. It might not even be your data, but it's existing data that is there and transformed. And this job is going to bring all those sources together and build a training data set for you. So we're going to let this one run for a bit. I think it's going to take some time, and I'll start to walk you through the rest of the code here while this one runs. So when this one is finished, you're going to have to read that file out. So we're still adding some syntactic sugar here, but for the time being, you need to read the data frame, sorry, the file out from the GCS bucket. And here's an example of what it looks like when it's done. You're going to have your existing entity data frame that we provided at the top here, this one, enriched with feature data. And an important thing that the feature store also does is it prevents you from, so it's going to scan back, right? So it's going to take each of these entities, like this driver ID and this timestamp, it's going to go to each of the feature tables and then try and find the actual feature value that it had at that point in time. But since the timestamps don't line up in almost any case, it has to scan back in time to find, what was the last known value for that feature. And it also, the feature store controls how far back in time you scan. Because if you scan infinitely, then it's an extremely computationally expensive operation. So, it's going to, you can control those dimensions. You can control how far back it scans. You can control how many features you want to add. You can control, how many rows you want through the entity data frame. But ultimately, you're going to be left with a data frame that you can use for training. So here's an example of training. It's super advanced model, just linear regression. And, you're going to have this model object at the end of the day. So all you need to do is, have your list of features and you have your target, split up your data frame, and you do your training. This is the part that, as an engineer, I suck at, and this is something that I leave up to data scientists. What we're trying to facilitate is provide you with a consistent view of your data, an easy way to, at scale, get data out of your feature store or your existing infrastructure. So this job actually ran and it's done now. But yeah, so that takes about, I think it took about, how long was that? 2.5 minutes or so. Okay, so, and then you can make a prediction, and we're just using the same data that we use for training. So this is obviously not a good practice, but you can see the model's trained and it is actually working. So now you've got a model trained, and at this point, what you typically do is, as a user, you'd ship off your model into ML flow. So you'd log it or save it for another team to productionize. It depends on the team. Sometimes, you're also the person doing everything and you're also productionizing it. But what you typically do is you'd save the list of features that you train the model on and with the model binary to ML flow. And then at another point, somebody can kind of deploy that. So, another step that's important to do is the ingestion. This is something that the job service will do automatically for you. But in this case, we're going to run these jobs ourselves. And so what we're doing here is running two jobs. And these two jobs are, for each of these two feature tables, driver trips and driver statistics, will load data from your upstream batch sources. Or, I mean, if you're running a stream, it'll be different. It'll actually provision a streaming job, load the data into your online store. So this is literally going to write from the upstream bucket into the Redis, and that's going to be your production serving environment. So these ones also take some time. It'll also take 2 minutes or so, and I'm not sure if it's worth waiting for them to finish. I just ran them right before I did this, join this call. So it's done, and okay, I just made a very big mistake because I reran this method which creates random entities. But okay, so now I can't run the rest of the cells. But essentially what you're going to have is, you're going to sample, I think this actually might be okay. So you're going to sample some entities, let's say a subset of them, because, this is typically what would happen in the production environment. You'd have an incoming request from a production system with like, some drivers or some users, and you'd want to enrich those IDs with features. And so you'd have a list of features, and you'd call the online Feast client with that list of features, and you'd get back your online feature values from production. So this is actually reading from Redis, and it gets it back at very low latency. In this case, it's with Python, it'll probably be 50 to 100 milliseconds, but we also have Java and Golang clients, and so in your kind of model serving environment, you'd have some kind of class, and it has some kind of initialization step where you construct your client for Feast, and then every time an incoming request comes into your model service, you just call out to Feast with this list of features that you already have, as part of that model binary that you've persisted, and you get your feature values, make your prediction, and then send the result back to your upstream system. So, as you from model's perspective, they only interact with Feast, right? So there's only a list of features, and there's, you get your feature values back. You don't have to have SQL queries in your model serving environment. You don't have to, in your model training environment, have direct access to Redis and all the stores and operational couplings. So it's a very decoupled relationship between models and data, and that makes it very portable. And with logging and monitoring and all the other things, you can start to install best practices into your kind of production environment. I'm going to stop there. Let's maybe just see if there are some questions that I can answer.
You know it. There are definitely some questions in here that you can answer. We've got one from Kumar asking about online feature stores average latency.
Yeah, I mean, that's kind of answered. The SLO that we had, right, the service level objective that we had at Gojek was 99p, which means 99% of requests at 10 milliseconds, and we complied with that. I'd say in most cases, 20 milliseconds is a good target that we can achieve at about 300 to 500 requests per second. That's with Redis, and it obviously depends heavily on the kind of amount of features you request, amount of rows of entities that you're looking up. We have variable length of types as well, so we don't just support like integers and floats. We also support things like strings or lists, and lists can be endlessly long. So we can't. It's very hard to make guarantees, but what we can guarantee is that it scales linearly depending on how you grow your data sets. And so, and the common SLOs that we hit at Gojek was 10 milliseconds. Yeah, with Java and Golang.
Nice. So the other question that a few people have been asking is, can they get their hands on this notebook?
Yeah, it's already open source. It's in the Feast Dev GitHub org. Yeah, I'll link to it at the end of our at this talk. Yeah.
Perfect. So for small businesses that are not using any cloud platform, can you still use Feast?
I didn't catch the first part. Just repeat that, please.
For a small business that's not using any cloud platforms specifically, can they still use Feast?
Well, I'd ask what the problem is they're trying to solve. I think the current implementation of Feast is kind of heavyweight, and it's something we're trying to address. We're actually working on something super exciting that's very lightweight, and hopefully will be easy for teams to just get started on. But often I'd recommend getting an MVP out, justifying and proving your business case, and then starting to slot in the feature store when you want to iterate and scale up. So if you're not running on the cloud, you're running on-prem, yeah, maybe you're maybe running at scale and you do need a feature store. But if you're just like two people and you're not even 100% digital, then I'm not 100% sure you do need a feature store. Yeah.
Just to reiterate that point, the work that Willem has done here to take a incredibly complicated thing and simplify it a lot is enormous. Slightly going beyond that, I think people put off implementing a feature store for a very long time because they don't think that they need it. And this is one of those classic examples of, unless you've seen it done well, you don't realize how valuable it is. And the funny part about it is, even in this notebook that you're looking at right now, you're going to see your implementation of a feature store, whether you realize you have one or not, right? Like virtually everyone I've ever come across is doing some form of transformation of incoming data. changing floats to ints or tokenizing things or anything like that. And feature stores are designed to do that. Now, that said, the work that, I've seen the work that Willem's about to do, to simplify, and I think it's tremendous, and I'm very excited to support him in public. And yeah, when you're getting started, getting to a feature store may be a little bit of premature optimization, but please don't think that you never need one. Virtually anytime you start to get to 1+ people on your team or want to productionize in any repeatable way, you really are going to need a feature store of some kind.
Agrees. That's great. Thanks, David, the comments. Again, just a quick reminder, if you have questions, keep posting to the Q&A. And if you want comments or you want to speak to ask questions, feel free to raise your hand. We can unmute you to ask questions or even comment on some of the answers. Please go ahead.
In terms of timing, are we still good for timing?
That's fine. We have a few more minutes.
Okay. Let me just try and wrap up then. I think that was the demo. I'll link to the notebook at the end of this talk, or I'll just paste it in this chat for Zoom. Okay, let me just present again. So, I mean, just to reiterate David's point, feature stores are becoming a critical piece of ML infra, and it's not just because it's a new thing that people can sell to you. It's actually valuable. Big companies realize this. The Googles of the world have already realized this 20 years ago, but you end up building something resembling a feature store whether you want to or not. And a lot of companies have started productizing and building these out for internal use cases and open sourcing ones like feature store and some other competitors of ours and other sister teams. So where are we now? I'm not going to take you through the whole roadmap and everything that we've done, but Fees has evolved a lot in the last year and a half, 2 years. It's come from a GCP only software that was kind of specific to some of the GCP tech, and we've work with Tecton and some of these major contributors to make it multi-cloud, add Spark support, and add a lot of functionality that teams really need today. And there's a lot of things that we think that still suck about Feast, and we really want to change. And I'm super excited about something that we're going to launch in about a month and a half and 2 months. We're trying to find folks that we want to become design partners with. So at the end of this talk, if you think that you've got use cases or things that you want to kind of build on a feature store with, just reach out to me. But yeah, so we've extended Feast for like the last year and a half, 2 years, and today it's a kind of a multi-cloud feature store. It runs on IBM, Azure, AWS, GCP, on-prem. There's a lot of different ways you can configure and deploy it, but it's still a heavy infrastructure system, and it's still something that you need an engineer probably to deploy. All of this thanks to some of the contributors that we've had over the years. Folks like Agoda and Postmates. They've contributed online stores. They've added security. We've had folks from Microsoft work with Farfetch and adding Feast into Azure using Delta. We've had Tecton contributing AWS support, and obviously the original Feast development was done in partnership with Google Cloud. So contributing and working with us and building out the community is like a massive thing that we're trying to do, and it's something that we really find super rewarding and super important to this project. And so just 3 kind of high-level things that are kind of core to our vision are, we believe in open governance and open standards. Right now, you'll see that there are some PRs and Feast where we're, shipping our data contracts and making them public and making sure that other feature stores also emulate them. We're, always want to be multi-cloud, modular, and production grade. And so right now, yes, we're, kind of cloud agnostic, which is good and bad. We're not specific to a cloud. Over time, we want to make it easy for you to just bring your own kind of managed services and make Feast very lightweight to use. And yeah, so we want to integrate with tooling of the future and specifically, the ML tools. So how we're going to do the governance is, we've entered the Linux Foundation, so we're now a top-level project in the Linux Foundation. We're part of Tecton. We're working with Tecton. So we're not officially, the project is not a Tecton project, but it's officially endorsed by Tecton, and it's, they're pouring a lot of resources into the project. They believe in the project, and it's something that they're trying to make a big part of. Just the tooling space, and something that a lot of teams use. And then finally, Kubeflow is a big important part for us as well. We want to be a core part of Kubeflow. We want to be deployed with Kubeflow stacks, and want to make it easy for data science teams to get a comprehensive end-to-end experience with Kubeflow. And we think Feast is a big part of that. So if you want to get involved, there's some links. Feast Dev, our homepage. We've got our GitHub repository there. We've got a new Slack here. The existing Kubeflow Slack has started to gobble up our messages, and so we've moved Slack, and we're excited for people to join there and just continue the discussions that we've already had. This deck is linked over here, tiny URL at Feast AI Camp, so you can go there and you can see this deck. I'm going to add the link to this notebook that I demoed and the link to the pull request where you can see the installation guide at the back of this deck right here in this list. And then to reiterate, we're working on something super cool and exciting. We're going to try and simplify and make Feast and feature stores easier to deploy. If you're on GCP or AWS, you've got online machine learning use cases, and you're thinking of using a feature store, reach out to me on Slack or on LinkedIn, and let's bounce some ideas. We can help you with your use case, and we want to just speak to some real users and just figure out like what problems you're trying to solve. All right, that's the presentation. I'm happy to answer more questions. Dimitri, are still there?
Yeah, I think it's kind of quiet here. I was waiting for a question to come through, but we may have exhausted the team. They asked all the questions they needed.
Cool. Okay, just head over to Slack if you have more questions.